All right, thanks everybody for watching, and thanks to the JupyterCon organizing committee for putting together this awesome conference. This session is all about high-performance Jupyter, and specifically how we can use tools like Dask and RAPIDS to make our data science workloads in Python faster. If you want to follow along, there's code here on this GitHub. Everything that I'm showing you is there. You can run it yourself now, or you can kind of check it out later. Quick about me, my name's Aaron. I'm a senior data scientist at Saturn Cloud, and my job is really all about making sure that data scientists can make their code run faster and work with larger data sets. If you want to contact me, there's an email there, Twitter handle and everything. I'm also an organizer for the PyData Miami conference. We're doing a lot of like virtual meetups and stuff right now, given the times, and then we're working with the PyData Global team to put on the virtual conference in November. So quick about Saturn Cloud, I'm not going to focus too much on this, but we're a data science platform in the cloud that enables people to take advantage of the full Python ecosystem and use tools like Dask and RAPIDS to accelerate their workloads. So the way I'm going to start this off is just thinking about some traditional data science that you might do with Jupyter, like on your laptop or on your single workstation. And these are the packages that you would use, right? Things like Pandas, scikit-learn, NumPy, the kind of tried and true, very mature packages in the PyData ecosystem. You launch up a Jupyter notebook, you import these things at the top, and then you get going with your data science. The challenge here is that these tools were written for mostly single core in-memory type work. So if your data set is larger than the amount of memory you have on your computer, you're kind of stuck. And then if you can load that data into memory, a lot of the times your computations might be really slow or might take a long time because you're just operating on a single core. You're not taking advantage of all the different cores on your machine. So that's our starting point. And then this leads into our discussion of high performance data science using Jupyter and the Python ecosystem. And that's where Dask and RAPIDS come in. These are the two tools we're focusing on. There's other tools to do like parallel computing or other things, but these are the best ones in my opinion, in working with Python and working with Jupyter, because they integrate really well with the Python ecosystem. And they're really, from leaping from PyData into these tools is not that difficult. So first thing, Dask. Dask is a parallel computing framework. So this means distributed or cluster computing. It actually works really well on your laptop to take advantage of all of your cores. On your laptop, it'll kind of create this little local cluster and then kind of simulate a cluster there. And so that way you're now using all of your cores instead of just one. But what's really cool about Dask is that it's completely written in Python and it was built for the Python ecosystem. So generally, if you have some Python code that's not running very fast, you can try to use Dask, and it's pretty easy to jump there and parallelize it. So it has low-level frameworks for parallelizing like arbitrary functions and custom code, but it also has high-level libraries like data frames and arrays that essentially wrap Pandas data frames and NumPy arrays and then kind of handle the distributed computing for you, as well as some like machine learning libraries and everything. But the key here is that you can run it on your laptop and then it'll scale up to a cluster. And I'm going to show you exactly that today. So RAPIDS is a little different when you're thinking about kind of making data science workloads faster. It's actually taking your computation from the CPU and doing it on the GPU instead. So Dask will parallelize like across a cluster, and then they'll use all their CPUs, just like all of the PyData tools are all operating in kind of the CPU area. RAPIDS was inspired by the performance improvements that people were getting by using things like TensorFlow and PyTorch on a GPU for deep learning, and then now is kind of making this accessible for the entire data science pipeline, data frames, arrays, other machine learning, and different things like that, all on the GPU. So here you get some like really crazy performance increases because GPUs are just way faster at number crunching than CPUs. So it is a newer library. There's a lot of stuff in there, and there's a lot of stuff continuing to be built up. But the key and this bottom point here is that when you run out of kind of GPU memory, because you now have to load all of your data onto a GPU, and you need to scale that like across multiple, RAPIDS integrates seamlessly with Dask. And so now you can scale to multiple GPUs on your machine or a cluster of machines that each have a GPU. And we're going to go through that latter case today. This is like a really kind of messy slide that I'm hoping kind of gives you some information about maybe when you're trying to choose one of these tools. The key is that you want to stay in the bottom left, right? If your data fits on your laptop, if your computations aren't taking a long time, stay there. There's no need to introduce any more tools. But if your data is pretty small and your computations are taking a long time, that's when you might want to think about switching over to a GPU using Rapids to get these really, really big performance increases. And if you're dealing with just like gigantic data sets, you might want to think about Dask for parallelizing this across a cluster. And then if you want both, you can use Dask and Rapids across a cluster of GPUs. So that's where you get like crazy performance increases and still able to operate on large amounts of data, which I'm going to show you today. So that's it for slides. Really, most of this talk is going to be jumping into the code and me showing you notebooks. So I'll just show you what the repo looks like for now. There's a summary here, which is basically showing you all the steps we're going to go through. We're going to go through like this whole story, right? We're going to start on our laptop. It's going to be slow. We're going to use Dask on our laptop to operate with larger data sets. It's still going to be slow because you're still on your laptop, but now you can deal with data sets that are bigger than what fits inside of RAM. So to get that to actually operate fast, we're then going to hop over to a cluster of multiple machines using the same exact Dask code and show how that operates really fast. And then swapping over to the other side, we'll start off with the Rapids with a small data set. So the idea is doing the same thing that we did on our laptop, except now on a GPU, and show how it's just like insanely faster. And then we're going to go to the large data set and then do a cluster, a GPU cluster with Rapids, and then kind of show how to do all those things. The cool thing here is that all of this code looks really, really similar. The Dask and Rapids APIs are meant to mirror things like pandas, NumPy, scikit-learn. So it's going to look really familiar. The imports are going to be a little bit different, and there's going to be considerations to think about when you're running on a GPU or running on a cluster. So the easiest way for you to get started, you can definitely run the first two notebooks on pretty much any machine that has like 4 gigs of RAM. When you go to a cluster, you need to switch over to the cloud, and I'm going to be using Saturn Cloud for that. And then if you have a GPU, you can run this Rapids notebook. But again, if you don't, I'm going to be running that in Saturn Cloud. And then the cluster of GPUs is a bunch of machines that you're going to need to run with. So this environment file here will get you going on definitely running the first two notebooks. You'll see the traditional workload we're doing, and then you're going to see the kind of how you can scale that on your laptop with Dask. So I'm going to start with that. I already created this environment, but I'll activate this, and then I'm going to launch up JupyterLab. So what's cool too is we're using these Dask JupyterLab extensions to do things as well. Let me make this window bigger. And so all these things are empty right now on the side. I've already kind of rearranged all my panes, but I'll show you that in just a second. The first thing I want to run through is just this laptop notebook. And I'm not actually going to run it because some of these pieces are pretty slow, but my assumption here is that you're familiar already with this code, and then I'm just showing you how you can extend it using Dask and Rapids. So not going to spend too much time here, but we're loading some New York City taxi data. It's publicly available on S3. It's really nice just because this data set is really, really big and it's free. So the full data set has something like 2 billion rows. We're going to operate with just dealing with data from 2019, which amounts to around 8 gigs of data on disk. Then when you load it, it takes a little bit longer. So, okay, we're going to do just that. So pandas can read straight from S3. We're using the S3FS package because we don't have any credentials for S3, or you might, but in this case, I'm not using any. And then we just load our CSV. So this downloads it from the internet, and then it reads it into pandas. So in memory now, this takes about 1.5 gigs. So not bad. It'll fit on most machines, and you can probably do the things that you need to. But it's a good amount of data, right? This is almost 8 million rows. So this is just all your stuff. So the workloads I'm going to focus on are like exploratory analysis, feature engineering, and then a couple different machine learning workloads. My exploratory analysis is just going to be this describe statement. There's more that you can do, of course, but this is a good one where there's a lot of operations happening and you can see it execute. So there's our describe. On a single month data, not bad, totally works. Here we're doing some feature engineering to basically extract some features and predict if people riding a particular taxi ride are a high tipper. So this means that they tip more than 20% for their ride. And here are some attributes. You can look at this later. I'm not going to go through it. But the cool thing is that you're going to see this function is going to be exactly the same code, whether we're operating with Dask or with Rapids. And then now this is what we're dealing with. We're predicting this. Okay, so we're going through two different machine learning exercises. One is hyperparameter tuning with an even smaller data set, because we're going to focus on just when you're compute bound, when you just have a lot of processing to happen. This is going to be a grid where you're just like slogging through and training a bunch of models. The model itself doesn't take that long to train, but you need to train a bunch of them. So in this case, we're going to deal with almost 400,000 rows, and then this is our scikit-learn pipeline to do that. We're going to try just some different values of the L1 ratio for ElasticNet using a logistic regression classifier. So we see here that a single model there took almost 4 minutes to run, and then our grid here with 15 different model fits took like 11 minutes. So not bad. If that's all you have to do, totally doable. And then the next workload we're looking at is kind of flipping it a little bit. We're going to use the full data, so in this case, the full month of data, and we're just training one single random forest. So this is a case where you have a pretty big data set and still a pretty complex model because the random forest needs to train a bunch of trees. So we'll do a train test split because we're not doing any sort of cross-validation, and then training a forest with 100 trees. So to fit that one single model took 2.5 minutes. Okay, again, if that's all you have to do, it's not. Spoiler, you're probably going to have to test some hyperparameters and do some other stuff, deal with other data sets. This can balloon to like hours, right, if you start to try a bunch of different things. But we'll say that's it for now. So the idea is then, okay, I dealt with a month of data. Now I want to analyze more data. Let's try to load in a full year of data. And this is where you probably are going to start to run into roadblocks if you're operating on your laptop. I have a pretty big machine here with 30 gigs of RAM. So this cell right here actually worked. But with pandas, what you have to do is literally just do a for loop and read each file, download them, concatenate them to your big data frame. If you don't have enough RAM, this is going to blow up, and it's not going to be a good time. If you do have enough RAM, it's still going to take quite a while, right? And then we haven't even done anything yet. So if we wanted to do a describe or train a model or all that stuff, it's going to take a while. So might feel you leaving like this, but the whole point of this talk is so that you can feel empowered and not feel scared by the big amount of data that you have. So the first thing I'm going to do is switch over to Dask on the same exact computer. So I'm on my same laptop, your laptop, it'll work. So what Dask does, like I said, is it parallelizes other Python objects. So a Dask data frame is a collection of pandas data frames. So because Dask operates in this cluster or distributed paradigm, it has to kind of like initialize that, right? So Dask, if you're running on your laptop, it'll actually create like a local cluster, which is like a fake cluster using the different cores on your machine. But this is good because with regular pandas, we would only be using one core. So this is where all of these panes on the right are going to start to come in. What's cool with Dask is it has this JupyterLab extension where you can actually just create a cluster right here from the side. So I can just click that new button, and now the cluster's up. You can see things start to light up here. So I'm actually going to do it directly from the notebook. So let me shut this down and then show you another way to do it, which is this first cell here, just importing this client and then initializing it. And then if I did initialize my client from the notebook, I can click this little magnifying glass here to connect to it, and then now it's kind of operating. So you can click on all these different buttons and it'll show you it'll bring up different windows and you can see different things. I pulled up a few and kind of already took the time to organize it here. So we'll see our task stream, and we're going to start to see some of this stuff light up as we do things. So the notebook here, I first show you the quote hard way to do it using the low-level Dask delayed interface. But I'm going to skip that for this talk. You can go through it and learn that. I'm going to stick to the high-level data frame API. So you notice this read CSV here looks very, very similar to the pandas read CSV. Sorry, my dog was being bad. So in this case, instead of loading a single file, we can actually use this glob syntax to tell Dask that I'm going to be loading a bunch of files. So I'll go ahead and execute this guy. Oh, I need to do some imports. Cool. So now this is going to load in those 12 files that took 16 minutes to load with pandas. But you notice that this cell only just took a second. That's because Dask is just maintaining pointers to where these files live. It doesn't actually do anything until you tell it to. It's this concept of lazy evaluation. Because the idea is that this data set does not fit in RAM. So what Dask is going to do is figure out all the things that you're telling it to do. And then when you go to compute something, it'll figure out how to load chunks into memory, operate on that, kick those out, load more chunks in, and then do a bunch of stuff. So when I go to print this data frame, it's not actually giving me any data because it's a Dask data frame. So what this does is it chunks the data into these 100 partitions, and then again, it'll operate on those chunks. And then you can kind of do stuff the same way you would do it with pandas, except if you actually want an answer, if you want Dask to trigger the computation, you have to do this .compute for most things. I'm not going to run this first cell, but I'll go ahead and run this describe. So you notice that this describe actually took 11 minutes on my computer, which is a long time, but it actually executes. If you tried to do it with pandas, you couldn't even load the data into memory. So I'm not going to sit here and wait for it, but I'm going to kick this off. And then you can see on the right that the Dask dashboard components start to light up a bit. So the first thing is that Dask figures out this task graph. So like I said, it's going to kind of know that it has to load a bunch of CSVs in parallel. It's going to get a data frame from them, and then it's going to start to do the operations that the scribe does. And then it'll do as many things kind of separately in parallel as it can, and then it's going to have to group things together because we're getting things like means and medians and like all that stuff, right? And then at the end, it'll give you an answer. So you can see, if you run this yourself, you can see that resources start to get used. You can watch the progress of all the different functions that need to happen. So, and then this cool thing is this cluster map telling you how data is kind of like shuttling around all your different workers. So I'm just going to kill this because we're not going to focus on it too much today. I don't want to wait for this really. We're going to focus on a lot of other stuff later. So what's cool here is that this feature engineering code, like I said, is exactly the same as the pandas code. No changes. And then this example is the hyperparameter tuning example. And so I'm going to show you this code, but I want to actually run it on the cluster so it'll run faster. But essentially, we're doing the same sample that we did from the other notebook just for, kind of timing comparisons. But you could do it with a larger data set. It would just, again, it would take a lot longer. But for now, before I show you this, I'm actually going to hop over into Saturn Cloud because I want to show you it running on a cluster. This will totally work. This notebook executes on my laptop. You can do it yourself. It's just parts might take a while. So again, there's a lot of options for kind of getting a cluster with Dask. This is just one option on Saturn Cloud that I'm showing you. So I have a project here with that's called Dask. It has a particular image that has all the packages that I need, and then I can hop into my JupyterLab interface. So now this is running on the cloud on an AWS instance that has 16 gigs of RAM. But the key here is that I'm going to use a Dask cluster now. So let me open up this Dask cluster. So Saturn Cloud currently, and I'm recording this in September of 2020, doesn't support the JupyterLab extension, but we're constantly adding stuff. So by the time you watch this, maybe we do, or soon after that we will. But the key here, the only difference between this Dask cluster notebook and the other Dask notebook is that I'm going to initialize a Saturn cluster now, instead of just that kind of local cluster with Dask. So now I'm going to say I want 5 workers of the same machine. So now I have 5 machines that each have 16 gigs of RAM. And then here's my cluster. And so to monitor stuff from Saturn Cloud, and you can do this with regular Dask as well, Dask actually has a separate dashboard UI that I'm going to go ahead and click here, and then you can see stuff. So let me actually rearrange some windows so I can show you the dashboard together. Okay. Great. So I actually like to use the dashboard separately because I'm normally operating on multiple monitors, and so then I can see it instead of kind of taking up my JupyterLab interface. Okay, so we're running the same code. So this is all the same stuff that I showed you before, except it's a whole lot faster to do stuff. Even just that kind of collecting the pointers was faster. So now this describe, we can actually run it here, and it's going to execute in just a few seconds. And so now Dask is now loading it. It's the same exact computation that I showed you before. And then we'll let that finish. That's going to take a few seconds. And then I'm going to run this. And then down here, we're persisting the data frame, which means now that I'm operating on a cluster, my data actually does fit in RAM across my cluster. On my laptop, didn't fit. Now I can run this persist command, which will actually trigger downloading all those CSVs. And then Dask will essentially like checkpoint the task graph that you did. And then it'll kind of hold all of that stuff in memory. So that way, then when you do stuff afterwards, it's going to be really, really fast. So actually, let me stop this one, and I'm going to show you that instead, because that's more important. Okay, one benefit of pre-recording is that I'm going to edit this part out because it's going to take 30 seconds. I don't want it to sit here awkwardly. Okay, great. So now we have our data frame persisted in memory across the cluster. We see that there's 9 gigs now across all of our different nodes. And then now when I want to do the length, or the describe, it's going to be super fast because it doesn't have to go to S3, download files, doesn't have to parse the CSVs and load them. It's all sitting in memory already, and now you can do things really quickly. Again, you couldn't do this on your laptop because you didn't have enough RAM. So now I'm going to run this hyperparameter tuning example. You notice that this grid search code looks very, very similar to the scikit-learn code. And then, except the difference is that instead of 11 minutes like it took on our laptop, in this case, it's just going to take a few seconds. And you can see the task graph of the kind of hyperparameter tuning happening. You can see the status and you can see things executing. It's really fun to just watch all the different colors fly by. But now, essentially, the same exact grid I did on my laptop in like 10 minutes, now just took 15 seconds across this cluster. And then you could scale this cluster out, make your grid a lot bigger, and it would still not take that long because it's operating in a parallel manner. So that's Dask, right? Now, again, okay, switch your brain. We're going to now swap over to thinking about not clusters, but thinking about a GPU. So I actually have another project here open in Saturn Cloud, which is operating on a GPU machine now. So this is, again, it's a machine in Amazon, but it has an image that has like Rapids and other different packages kind of installed already. So now that we're going to operate, thinking back to the laptop notebook, we're going to operate with this small, like single month of data, except now on a GPU instead. So we can open up this Rapids notebook, and actually there's also a dashboard. There's another JupyterLab extension called the JupyterLab NV dashboard, which is put out by the Rapids team to actually monitor your GPU utilization from within JupyterLab. So I'm going to click this GPU resources one, collapse this, and then we can see things happening here. Awesome. So now you can see what's happening with your GPU. In this case, we import the cuDF package, which is essentially pandas on a GPU. The API, again, looks very similar to pandas. The team treats it if cuDF can't do something that pandas can, it's a bug, and they're going to fix it and add it. So now our loading is exactly the same, except now instead of like a minute that it took on our laptop, now it only takes a few seconds because it's just faster. It's crazy to think that loading a CSV is faster on the GPU, but again, all the stuff that's happening is just number crunching. It's got to figure out stuff. It's got to kind of convert data types and like do all this stuff. And GPUs are just really good at doing that type of processing. So now all of these commands are just like instant. Whereas on my laptop, it might have taken some time to run. Even this describe, look at this. This describe takes 800 milliseconds. On my laptop, it only took 4 seconds, but you can kind of see how like the difference in performance. It's pretty cool, and then we can see things happening here. So again, this feature engineering code is the same. The only difference here is the API is exactly the same. The only difference is I have to convert it to 32-bit precision. So I'm doing a float 32 and an int 32 here. But again, all the other stuff is exactly the same, but just because we're operating on a GPU, the random forest machine learning needs the 32-bit precision. So same thing, instead of scikit-learn train test split, we open up the cuML, which is Rapids machine learning library. If you haven't noticed the pattern, everything starts with cu for CUDA, right? And this random forest looks the same, except now, I already spoiled it, but you run this, it only takes 1 second to run, to train this random forest with 100 trees, whereas on my laptop, where's that JupyterLab? On my laptop, the random forest took, let's see, the random forest took 2.5 minutes. So now you can start to layer hyperparameters, you can start to do a bunch of stuff, and you're gonna see where like it's just way faster to operate on a GPU. So I hope I convinced you that it's worth it, and it's like not even that expensive. On the cloud, this GPU instance costs like 50 cents an hour to run. So it's like a no-brainer to run this stuff on a GPU if your data will fit into GPU memory. So that's the key, right? GPUs tend to have less memory capacity than a computer, right? I can launch an EC2 instance on Amazon that has 500 gigs of CPU RAM. But the biggest GPU I can get currently, as of September 2020, is 16 gigs of RAM. So if I wanted to operate on larger data sets that aren't even really that large, or just like a little bit large, I need to now scale across a cluster. And that's where Dask plus Rapids comes together. And I'm going to stay on this same machine actually, but I have another notebook now that's initializing the Saturn cluster in the same way, except now you're running a cluster that has GPU instances. So now I still initialize the Saturn cluster, but now my worker is this G4 DNX large, which is this Amazon machine that has a GPU. So if I run this, now I can see that this 46 gigs of RAM is actually those 3 GPUs, right? So again, we have a dashboard here. I'm going to click on this link and then bring it over to my other tab. And so now this is actually executing on the GPU instead. So Dask also has a couple other like currently hidden pages where you can monitor GPU utilization and memory and things like that. And so that I provided a couple links there for you, but we're not really going to do that right now. The key here is now we're importing a different library. It's called Dask cuDF. So this is the cuDF thing, everything's operating on a GPU, except now Dask is handling orchestration to do this across a cluster. So now this code is going to look a lot closer to the Dask code. Again, all of these notebooks look very, very similar, but now instead of kind of loading a single CSV file, I'm using the same glob syntax to load all of them, right? And again, Dask isn't doing anything yet. This is just a pointer because now we're using Dask to control GPU RAPIDS data frames. So I can execute this, and so we can see now again that this task graph starts lighting up, and then RAPIDS is loading all 12 of these CSV files, doing all this processing, and then computing the row counts and the memory size. This is something that took, let's see, on the Dask cluster, let's see how long this took with the CPU. This took a minute on the CPU with the Dask cluster with 5 machines that each had 16 gigs of RAM. Now I'm operating just with 3 GPU machines, and this executes, I think I saw, in like just 30 seconds. So that's good. You're still getting your performance increases. And the next thing we're going to do, again, it's the same exact feature engineering code. We do the persist in the same way like I showed you on the Dask notebook, except again, this persist just happens faster because everything's happening faster because we're operating on GPUs. And so again, what this does is it's loading all the CSV files, it's processing them, executing that task graph. So that way, when we go to train the model, we know that we're just timing the model training time. And again, this code looks exactly the same. As of the version that I'm using of RAPIDS, there's not a train test split implementation. I'm sure it's coming soon. This is the distributed one, right? There was one for the regular kind of QML package, which was operating with a single GPU. But since we're using the Dask one, there needs to be a different distributed implementation. So I'm sure there's one coming, or if you want to contribute it, that's totally awesome too. So now we're dealing with 10 times the amount of data that I was showing you in this RAPIDS notebook, because it's the full month. It's really 12 times the amount of data, full year, excuse me. But it still operates in just 5 seconds. So that's pretty crazy, right? I'm dealing with like how many rows here? Let's see. We're dealing with 85 million rows, training a random forest with 100 trees in just 5 seconds. So that's where I'm going to leave it. And I think that's really exciting. Again, you can grab this code and check it out. Reach out to me if you have any questions. I'll put my contact info here again. But all the slides are available. And I hope you have fun checking this stuff out. Thanks for watching.